So, good morning. Welcome back to Krishna's classroom. It's after a few months that we are once again giving a talk on this channel. And in fact, if you recall, we had been working on determinants. The objective was clear. What we wanted to do was just give a um, a structural reason or structural analysis of what determinants are. We have completed most of the work except the last part, namely the general case, what exactly a determinant is. And we have explored the cases 2 and 3 to get a feeling of the problem. And in this context, we also come across functions on the set 1 to n, especially the class of permutations of the set of integers 1 to n. So we did a special talk on permutations. I think, if I am not wrong, I think we concluded our last lecture was on these preliminaries. Now, since it's after a long time that we are taking up this, maybe after about 3 or 3.5 months that we are looking at this, maybe we just repeat some of the things that we had looked at to get a feeling of the problem. Now you recall that we come across determinants as a very handy notation in the context of solving simultaneous linear equations. And then we observe that the solutions can be expressed in terms of ratios of determinants, and which also tells you under what conditions the solutions exist. All these questions can be looked at by looking at the property of the determinants. Curiously enough, the definition of the determinant is not something straightforward, but very fascinating, and with remarkably fascinating properties, as we shall see soon. Now that, of course, leaves the question, what exactly are determinants? Apart from the definition that we make, what exactly a determinant is? Is there any deeper structure related to it? We should suspect that there is some deeper structure because something very elegant and beautiful is happening there from the definition. Therefore, we should suspect that there should be something very elegant. There should be a very elegant structure which works behind it. And our objective of these lectures is not just define what a determinant is and then write down the properties of the determinant, but to explore what this particular structure is. And that's very fascinating. In fact, we have nice things, objects like what are called n-linear forms, etc., coming into play. So let us, as I said, apologetically, since I am lecturing after a long time on this topic, possibly it may be worthwhile to recall some of the uh, the special cases get a feeling, and they appear in the first 3 4 lectures. So this is the seventh one, and let me just recall them and try to introduce the right type of notations so that your passage from case 2 n equal to 2 to general n is going to be rather very transparent. Okay, let us start there. Now let me start with the uh, definition of an n-linear form of R. So we take x to be fixed notations. Now we define a n-linear form as a map from x to R. It's a form. And we say it is n-linear in the sense that, see, this is what happens. You take x1, xn belonging to x, it gets mapped to what's called f of xn. This belongs to R. Now this is not an arbitrary map, but having the following properties. With the following properties. F is linear in each of the arguments xi, keeping all other this means the following, that is f of x1 xi minus 1 xi plus xi tilde xn equal to f of xn plus f of xn. This is one property. The second property is that f of cxi xn equal to c times xn. So these are the two properties that f should satisfy. Now that is for every I belonging to, that means if it's I, then f is linear with respect to xi when all other xi's are, xj's are held fixed. Okay, then you say f is n linear because there are n arguments here, therefore this is an n, this is what you call an n linear form. An n linear form. So that is the definition of the n linear form. Okay, because we want to look at determinants as a special class of linear forms that we will see soon. Okay. Now what we want to introduce, there are certain notations that are needed for our work. Let's okay. Now we denote by Fn some notations. Let Fn denote all functions defined on the set that means phi belongs to Fn phi is a function from this is in general. So you are considering all functions from defined on the set 1 to n. That means phi I may be equal to phi j. Okay. So you got phi 1, phi 2, etc., phi n as the images, and some phi I may be equal to phi j. That's possible. Okay. So this is a map that you, this is a collection of maps that you consider, which also includes those maps which are 1 to 1, or what you call which are all. So that's it. Yeah. Now let me denote by the set of all one-to-one functions on these are essentially permutations of so this is the situation that you have. So we have a few things now that Fn we have defined. Then you have what are called PNs, the permutations. This we shall need for our later work. Now we define E5 as E51, E52, E5. So it is quite possible that some of them are repetitive because I am going to take 5 to be a element of F. So how many elements are there in Fn? Many functions are there in Fn. Now you see that there are n to the power n functions that you can have on this class. Okay? But the moment you restrict Pn is a subcollection of Fn. The moment you take Pn, we have n factorial functions. Okay, so note that this one, and there are n to the power n elements in Fn, and there are n factorial elements in Pn. Now this we shall keep in our mind as a notation. Now E5 we consider for all these cases. Okay. Now we also introduce the following notation, namely E5 tilde. So we write EI tilde as a linear function Rn such that if I delta x, that means Ei tilde Ei equal to 1 and Ei tilde Ej equal to 0 whenever j is different from, that's the standard Kronecker delta rotation. So this is for all now we write Ei tilde or E phi tilde define this as, this is not just a mere notation which has some meaning that as we shall see soon. E phi 1 tensor notation, but we don't have to go the deeper meanings of this. It's a convenient notation that we use. E incidentally, let me just remind you that in my previous lectures, instead of E tildes here, I have simply used E with this notation. Doesn't matter, but make some convenient. This writing would be then a problem. Okay. Let us now this is for every and this has a property such that if the action of E phi tilde on E psi equal to multiplied by etc. E psi. Okay. Now you see that from this property, it's easily seen that this is equal to 1 only when phi 1 is equal to psi 1. This is equal to 1 only when phi n equal to psi n. Now this is a product of n factors. Now if one of the n factors becomes 0, that means if phi j is different from psi j, then this product is going to be 0. That means if phi is different from psi, then this evaluation is going to be 0. Okay? And this evaluation is equal to 1 whenever phi is equal to j. So note that. One whenever phi is equal to psi and this is equal to 0, psi. Now this is an important feature. So we have introduced certain objects called E phi tilde in this problem. Now this we shall need while developing the theory later. Okay. Now one observation that you make is that the following. First make an observation. So f is an linear form. Then it has a certain structure. Let me do that. Okay. So let me work on this. So we have the following theorem. Alright. Then n is a linear combination of E phi theta. Now this is something very crucial which would work throughout this lecture, this particular problem. Okay. Well, we prove this. Let x, where each xi belongs to then we look at this. F of x1, x2, etc., xn is going to be equal to f of summation over j aij a1j summation over j a2j ej summation over J because you see that we are taking x1 is in Rn, therefore x1 is a linear combination of E1, E2, etc. En. So also every argument. So we are just writing this and they are determined by the coefficients A, I, J. So the set of coefficients A, I, J determine this particular linear, these vectors uniquely. Now we have assumed that f is linear in each of the arguments if you leave all others fixed. Now you go about doing an expansion. Then this is what you end up with. Okay. So what you get would be something like this. So if you just take expansion on one of the components, the kth component or something, then you are going to get f of equal to summation over, let me write x1. So you have what? Yeah. Etc. K minus 1, then AKJ. So you have essentially AKJ coming out. Like this. It is summation over AKJ f of EJ x. Because you have a sigma AKJ EJ coming. So that we pull out, the coefficient would come out and write this. So we have used the linearity of f on xk. And now this is summation over j. Okay. Now what we have? We do it with each one of these xi's. Okay. So you see that essentially this will become summation over E, what you call sigma. How many summations are there? There are n sums that come. So eventually I will just put everything on one sigma and write the whole thing in the form of following this as sigma A1 Y1 A N N of f of E phi 1 E final, where phi belongs to F. Okay. What does this mean? Therefore, this is equal to sigma summation over phi belonging to Fn A n phi n f of E phi. So this is the sum that you end up with. So there is a scalar multiplied by f of E phi. These scalars come from these aij's. Okay, and the summation has to be taken over all phi's. So this is what you end up with. Okay. Therefore, what it turns out to be is that the statement that we have made. Okay, we'll come to that. We have got a linear combination coming up like this as a sum. Okay. Now we will try to work out this. What A1 phi 1, A phi A n phi n etc. is. Okay. Let us work it out. I'll give a demonstration with n equal to 2, then everything will be clear. But before that, we will work out this. Now let us compute this. Okay. E phi tilde of N. Now E phi tilde being extended to the whole Rn as a n linear form. We'll just work this out. Then this is going to be equal to sigma E phi tilde of that will give you, that This will give you simply A1 product of this. Okay. Now, if you put psi here, then you see that it's the corresponding. Okay, let me use here psi, the general form. Then you see that this is what you have, and you see that E tilde psi E phi equal to 1 whenever psi equal to phi. Otherwise, it is 0. So if you use that, then this is what you. Okay, use that property, and then this is what you. So let me just write this A1 this is equal to E so let me write this now. Therefore, what do we have? We have f of this is equal to f of sigma f of E phi to E phi tilde acting over now this is the relationship that you get, and this is true for every belonging to now this is the crucial result that you have. So what does this indicate? This implies that f is essentially equal to sigma f of phi times E phi. Therefore, you see what exactly is this form. So this has been rewritten in terms of E phi tilde, and this is exactly in terms of this we can rewrite this. And f E phi will turn out to be essentially the coefficients. So it's a linear combination of these E phi tildes, and that's a beautiful result because it helps us a lot to understand this particular n-linear form. Now let me just demonstrate all this. That completes the proof of this. Okay. Now we try to work an example in case n equal. So let us consider the special case n equal. Then what do we have? See, let me keep the theorem here. Let me take out the thing. Okay. So we are considering x equal to so now f is x1, x2 is such that f is linear in the first argument, f is also linear in the second argument. Each of the two arguments when the other is fixed. Okay, so you see that x1 is essentially equal to a11 e1 plus a12 e2. x2 is equal to a21 e1 plus a22. Therefore, let us write down what fx1 x2 is. Now this, of course, if you use the two linearity, f is two linear, hence we have f of equal to a11 a21 f of e1 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 plus a11 a22 a12 a21 f of e1 plus a11 a22 a12 a22 This is what the expansion turns out to be. Now let us compute what a11 a21 a12 a21 a11 a22 a12 a22 these coefficients you compute. For convenience, let us write E11 tilde we define as acting over Eij delta IL delta J. For I, J, K, L, then what you get? You have four entities. One is called E11 tilde, E22 tilde, E12 E there are four such entities. Are defined using this. Now this is the property that E11 tilde acting over E11 is equal to 1. Otherwise, for on all other Eij it is 0. Similarly, E21 tilde acting over E21 is 1. All others on all others it is 0, etc. So that is quite easy to see what happens. And if you work this out, this is what happens. So f of now you can easily work this out. So what is this? This is equal to, this I rewrite as this is equal to A11, A21, f of E1 is f of E11. Let us use this notation. I'll translate into this five form soon. Plus A12, A21, f of E21 plus A11, A22, f of plus A12, A22, f of this is our notation. Now instead of f, okay, so let us work out this. Assuming each E11 tilde is a two linear form, assuming each Eij determines a two linear form, we have E11 This is equal to A11, A21. E21 A12 A21 E12 tilde acting over X1 into and E tilde E22 equal to A12 A2. Now this is what you have. Okay. Therefore, I can write F as, now you see I replace this one. Therefore, it follows that F equal to, what is it? This is, okay, F of E11 E11 delta plus F of E21 F of therefore this simply becomes a linear combination of E11 tilde, E21 tilde, E12 tilde and E22 tilde. Okay. Now let us look at these maps. Okay, let me just replace this so that you will get a hang of it. I suppose all the computations are right, or if there are some errors, you correct it. Essentially, I think I have not made a mistake. Hopefully, you can see. Now, what I do is, see, 1, 2, you have these maps. Into 1, 1. Call this, okay, let me call this 1, 1. Okay. Then 5, 5, 2, 1. Okay. From 1 to 2, what you have? 2, 1. Five, 2. 5, 1, 2, into 1, 2, then 5. Now here you see that this means 5, 1, 1 of 1 equal to 1. 5, 1, 1 of 2 equal to 1. That means it is not a onto map. 5 to 1 of 1 equal to 2. 5 to 1 of 2 equal to 1. This is a 1 to 1 map. Then you have 5, 1, 2 of 1 equal to 1. This is the identity map. 5, 1, 2 of 2 equal to 2. Okay. Then you have 5, 2, 2, 1 equal to 2. 5, 2, 2 of 2 is also equal to 2. So this is not a 1. Okay. Or if you want, you can even write this as phi, psi, chi, and some other notation. Okay. Now these 4 maps are significant in this regard. I mean, they take care of all maps. So what you call F2 consists of these are the 4 maps that you have. This 2 square different maps that you have. So they come. Okay. So this can be eventually using this notation. You can write F as summation over 5 longitude to E 5 theta operating over, or I can write this way, F of this is the form of it. Okay. Right? So this is exactly what I did until now. Okay. So that's about the structure of the n-linear form. Now you see that, I have phi 1, phi 1. Okay. See, I have phi 1, phi 2. Phi 1, phi 2 is 1, 1. That's what I am writing. So phi 1, 1 is phi okay. Actually, so what you call E phi corresponds to E phi 1 E phi 1 E phi. This is the definition that you have. Then you get all these things. This is how you write as this. Now sum over all the possible phi's that you have. This there are 4 such phi's, so you are summing over that. So you get the result. So this is the result that we have put. Okay. Now this is about a linear form. So what an linear form turns out to be is merely a linear combination of what is called E11 tilde, E21 tilde, E12 tilde, and E22. So that is an advantage because it's nice to evaluate this on EIs. So that's the advantage. So we will, I think at this stage, I think stop this. Okay. And what we want to look at next is the alternating and linear forms. That is a special class of linear forms. In that case, what advantages do we have? We have already looked at it earlier, but we will recall it and look at it in the context of these notations that we have used. Okay. So here f is any linear form. Now we are going to choose alternating a linear form. That means a linear form on Rn with some specified properties. Okay, and it has got something to do with vectors basically, with the determinant that we are going to choose. So we will work it out in our next lecture. I want to go rather slowly on this. This is not. I think that's enough for the day. Thank you very much.